Okay, friends. So we got one last class period before your exam starts. Starts tomorrow, ends Friday. Pay attention, please, to the testing center website hours. I think Friday last test is handed out at 5 and collected at 6. So make sure you have enough time to do that. Let's see. So we've been through all of the basic electrophilic aromatic substitution reactions. So there are 5 of them: halogenation, nitration, sulfonation, and then the 2 Friedel-Crafts reactions. As we were doing that, I pointed out where there are things you can do synthetically to the functional groups that you introduce. Not a lot you can do synthetically to a bromine or a chlorine once it's on, or a sulfonyl group once it's on, but thinking about the nitro group, which you get from aryl nitration. Once that nitro group is there, you can reduce it using palladium catalyzed hydrogenation conditions. You can reduce it to the amine. The amine attached to a benzene ring is called an aniline. So you might read that in the text or hear me use it. And then you can do with this aniline some of the same basic things you can do with any sort of amine. So you can do, for example, acylation of the amine to make an amide bond. And there are multiple ways you could do that. I just provide one of them here. You could make imines. And let me see, you could probably also alkylate the amine to generate an alkyl aniline via sort of an SN2 reaction. So there are multiple things synthetically that you can do with anilines, and the nitro group can be a path to that. Why am I doing this? Well, I'm trying to prepare you for synthesis problems that you may encounter where you will need to look at something like, and I'm sorry I didn't actually draw an imine, I guess you'll have to just imagine that, what the imine is. But I'm hoping that if you see things like this, you can be thinking, all right, that could have used to have been the aniline, which could have used to have been the nitro group. Similarly, with the Friedel-Crafts reactions, there are downstream things we can do once the reactions are done. And I'll show you just a few of those, and this will be maybe a review. We'll start out with Friedel-Crafts alkylation. It turns out that as long as you have at least one benzylic proton, there's some interesting things that you can do. So this proton is called a benzylic proton. It's at the benzylic position. It's adjacent to a benzene ring. And so if you have one of those, at least one of those, there are some things you can do. One of them is called radical bromination, or we'll just say radical bromination. This isn't new. This is a review of a reaction that you learned in 351 in the chapter on radicals. And you learned that bromination was selective for the more stable radical. If you look at this molecule, there's lots of CH bonds that we could consider abstracting with the bromine radical, but if we abstract one of the benzylic protons, we're going to get the resonance stabilized benzylic radical. I won't draw that mechanism, but you can, if you review the radicals chapter from 351, you can envision what it would be like. And then that benzylic radical will react with some of the remaining molecular bromine that's present, and that installs a bromo group at the benzylic position. And of course, there are all kinds of things you can do with bromo group. This is basically 351 chemistry. You could do elimination to get an alkene. You could do substitution to put some nucleophile at the at the benzylic carbon. And then there might be downstream things you can do with that nucleophile. So, again, I want you to have the idea that if you see benzene rings with these kinds of groups on them, you should be thinking, I could have gotten that from the benzylic bromination of the Friedel-Crafts product. Now, that's not the only thing you can do with the alkyl group, and again, I think we talked about this last time. As long as you have at least one benzylic proton, you can use a reagent called KMNO4, that's potassium permanganate. It's a really it's a pretty high-powered oxidizing agent. The mechanism isn't presented in your text. You don't need to know what it is. It likely involves radical chemistry because you need at least one benzylic proton for this to occur. But KMNO4 breaks all of the bonds between the benzylic carbon and the three things attached to it. So it's going to break this one, and this one. And it's going to replace all of them with carbon-oxygen bonds and give you a carboxylic acid. That's pretty dramatic. It seems like magic chemistry. We're not going to talk about the mechanism. This is probably a memorized reagent. You need to be aware of it, though, because if you see a carboxylic acid attached to a benzene ring, this is probably how your text expects you to do it. Okay, I think that's all of the sort of after-the-fact reactions that you can do with Friedel-Crafts alkylation. Questions so far? Yeah.
Can you put the carboxylic acid on there if it's just an alkyl group, or does it have to be an ethyl group?
Could it be any alkyl group? It could be any alkyl group, yes, as long as you have one benzylic proton. So if this were a tertiary carbon, KMNO4 wouldn't work. So says the text. Okay, others? All right, let's look at Friedel-Crafts acylation. This is putting on the acyl group, which is basically a carbonyl. Your starting material is an acid chloride. We'll just put an R group there. Of course, the product is this ketone. Usually the R group here is an alkyl group or an aryl group. Some people look at that carboxylic acid and they think, oh, I could have done that via Friedel-Crafts acylation. Let's just use this reagent, which they invent. And that reagent actually exists, but the preferred method for making the carboxylic acid is shown here. Generally, Friedel-Crafts alkylation gives you ketones. And then, what can you do with the ketone? Well, you can do reduction to an alcohol, right? You can reduce ketones to secondary alcohols. What else have we learned to do with ketones? Well, you could do a Wittig reaction where with a Wittig reagent where you install some kind of pi bond between the carbonyl carbon and then the carbon of your Wittig reagent. Sorry. All right. Let's see. You can make imines with ketones. Trying to think what else. And then you can, of course, do nucleophilic addition to carbonyls where you have some other R group attacking the carbonyl carbon to give you an alcohol. And that's interesting so far. There's another thing you can do which with the ketone, which is going to seem like something of a step backwards. This is a new reaction just introduced in chapter 20. There are two different conditions for it. I don't honestly know why they give you both. It's like they just want to make you memorize more reagents, and it's kind of a pain. I'll show you both of them. This is a ketone reduction, but it's not a reduction of the ketone to an alcohol. It's reduction to an alkane. So what we're saying is we're going to replace both of the carbon-oxygen bonds in the ketone with carbon-hydrogen bonds. Okay, and there are two different conditions that do this. Option one, which works, is zinc and HCl. Zinc metal can reduce the ketone. The mechanism we're not going to talk about probably involves single electron transfer from the metal to the pi star of the ketone to get started. That's one option, and that's probably a memorized reagent. Option two, and some of these reactions have names which we won't bother worrying about. Option two is to use hydrazine and hydroxide. The mechanism for that reaction is known, and it's not hard, and it's kind of cool. If you want to see it, we can talk about it sometime, but it's probably beyond the scope of the class. So, perhaps the ketone is the one with the most different places that you can go, but when you see these kinds of functional groups attached to a benzene ring, you need to be thinking, I could have gotten there through a Friedel-Crafts acylation reaction. Now, why on earth would you ever, if you have the option to put an alkyl group on directly, why would you instead choose to put the acyl group on and then reduce it to the alkyl group? There's a reason for this that's described in your text, which we are dodging completely. Your text points out that some alkyl halides undergo problematic carbocation rearrangement. And I've told you not to worry about that. So we're going to blithely pretend like that doesn't exist. However, your text doesn't, and so there are some alkyl groups that you can't put on via Friedel-Crafts alkylation if you want to avoid carbocation rearrangement. And the convenient workaround is to just put on the acyl group and then reduce it to the alkane. We're not going to worry about that in the sense that I've told you not to worry about carbocation rearrangement. However, there is another reason why you might want to reduce to an alkyl group, and that won't become apparent until we start talking about the impact of putting multiple groups on a benzene ring and the concept of regioselectivity. All right, with that, cheers, excuse me. All right, with that review of what's going on synthetically and what our options are, what questions do you have? Okay, well, let's now talk about all of our starting materials so far for these reactions have been benzene. Let's talk about what happens when a group is already on the benzene ring. So let's suppose that you have already previously done a Friedel-Crafts alkylation to make. Why you did this instead of just buying the bottle of toluene, I'll never know, but this methylbenzene is actually called toluene commonly. And let's imagine doing a nitration reaction on this product. So that's just HNO3 and H2SO4. Now you can see that, when benzene was our starting material, all the carbons were identical, so it didn't matter which one the electrophile went on. Now I have 3 different carbons in my toluene starting material. I have what's called the orthocarbon, which I will abbreviate with the letter O, the metacarbon, which I will abbreviate with the letter M, and the paracarbon, which I will abbreviate with the letter P. This is how we talk about benzene rings. Ortho, meta, and para are relative terms. They all refer to ortho meaning adjacent to the methyl group, meta meaning 1 carbon away, para meaning 2 carbons away. So we now have a choice, and we need to consider the possibility of 3 regioisomers, one of which is to have the nitro group on the orthocarbon. Is that going to bother you that I put it on the other side? I don't care, just deal with it. Or on the metacarbon, or on the paracarbon. These are the 3 regioisomers that you could possibly get. Again, we'll call this the ortho isomer, the para isomer, and the meta isomer. And it turns out if you want to name substituted benzenes, you actually use these terms. This would be called orthonitrotoluene as an example. But it turns out that in the case of the methyl group, we actually observe the ortho and the para, but not the meta isomer. So it looks like there is some regioselectivity for where the electrophile attaches, and we need to try to explain why. It turns out, however, that regioselectivity is not universally for ortho and para isomers. If I have, suppose I decide to start with nitrobenzene, and then I want to do the chlorination reaction, again, I'm going to have the possibility for ortho, meta, and para products. But for the nitro group, it turns out that what I observe is just the meta product, and is just the meta product and not the ortho and the para products. So the point is that the group that is already on the benzene ring influences the regioselectivity. We sometimes call these directing groups. Groups like the methyl group are sometimes called ortho and para directors because they preferentially give you ortho and para isomers. Groups like nitro are called meta directors because they preferentially give you the meta isomer. So we need to explain this and then exploit it for our purposes. So the explanation works best if you understand the mechanism of electrophilic aromatic substitution. Remember that that involves addition of the electrophile to one of the carbons of the benzene ring. And we get a high energy carbocationic intermediate. So you expect the first step, and you're breaking aromaticity, right, when you go from this, and I'm not going to draw the push arrows, I'm going to draw intermediates. And let's draw the intermediate for This is the addition step of electrophilic aromatic substitution. I'm going to be general and just use the letter E for electrophile. I'm going to show you the intermediate that you would get for ortho substitution. So that would put the electrophile on the ortho carbon and put a positive charge there. So that's the ortho intermediate. This is an uphill in energy step, right? You're breaking aromaticity, you're forming a high energy carbocation. And so we would expect that this step would be faster if it led to a more stable carbocationic intermediate. So let's now draw the meta substitution intermediate. And then let's draw, oops, that's meta. And then let's draw the para substitution intermediate. Now, at long last, you should be having an aha moment where you see why on earth, if you took 351 from me, I beat you in the head, not literally because this is not a violent class, but on the test, I repeatedly had you think about where charges could be delocalized by resonance. We're going to highlight in pink places where the positive charge can be. For the ortho carbocation, it's on those 3 atoms. We're not going to draw those resonance structures. If you want to come back and do that, you can. You should convince yourself that by resonance, the positive charge is delocalized on all 3 of those atoms. Similarly here and here. What do I notice? What is different about the ortho and para isomers, intermediates, that is not the same as the meta intermediate? What do you notice? So in the ortho and para, you guys are noticing that the positive charge can be, now some of you are saying, oh, that's a tertiary carbon and tertiary carbocations are stabilizing. That's a decent way of thinking about things. The other way you can think about things is to consider the character of this group that is adjacent to the positive charge and how does it affect this positive charge, okay? It turns out, for reasons we've discussed previously, alkyl groups in general are electron donating groups. So we'll call that EDG, and the reason for it is the inductive effect. What do I mean by that? I mean that an sp2 carbon here is more electronegative than an sp3 carbon. So there's actually a dipole that pulls electron density away from the CH3 and toward the benzene ring. Therefore, the ortho isomer has an electron donating group on a carbon that's electron poor. That should stabilize the carbocation. That makes sense? Anything we can do to spread out positive charge is good. Putting an putting an inductive electron donor adjacent to the positive charge is a stabilizing effect. So the ortho intermediate is more stable due to the electron donating group spreading out the positive charge. And that's true for the para isomer, not here for the meta isomer. The positive charge isn't adjacent to the methyl group, so the impact of that methyl group is less. So of the 2 options, the meta and the para carbocations are more stable. That means the reaction that leads to the ortho and para products is faster. And so we tend to see only ortho and para products there. The methyl group is an example of a the methyl group is an example of an ortho-para director. Okay? Yeah,
Is that true for just methyl groups or for all alkyl groups?
that's true for all alkyl groups. Yeah, generally true for all alkyl groups. Let's now look at the explanation for meta regioselectivity. Again, we're going to think about the addition step and draw the various intermediates. So here is, oops, making stuff up at this point. Here is the nitro group, which I'm going to draw out its Lewis structure. Here is ortho substitution, so the ortho substituted intermediate. Here is the meta substituted intermediate. And then here is the para substituted intermediate. All right, let's look at where the positive charge is for the ortho, meta, and para substituted intermediates. Again, we'll highlight that in pink. For ortho substitution, it's there. For meta substitution, it's there. And for para substitution, it's there. So you can see that both the ortho and the para isomers place the positive charge on a carbon adjacent to the nitro group, whereas the meta isomer places the positive charge not adjacent to the nitro group. So clearly this is influenced by the nitro group. Let's look at what the nitro group does. We're going to call the nitro group an electron withdrawing group for a couple of reasons. First, nitrogen is more electronegative than carbon, so this is an inductive electron withdrawing group. You're also going to see that the nitrogen is a resonance electron withdrawing group. Okay? What does that mean? Well, to see that effect for resonance electron withdrawing group, you almost need to just look at the nitrobenzene to begin with before we even do the addition step, and think about what that does to the benzene ring. So, and electron withdrawing groups by resonance often have this pattern of a pi bond to an electronegative heteroatom adjacent to the at the benzylic position. So this is the benzylic position, and it's doubly bonded to an oxygen. When that happens, you can do the following with arrows to generate another resonance structure. And this resonance structure would tell you that actually for nitrobenzene, the ortho and para carbons are electron deficient to begin with, because the nitro group by resonance can make the benzene ring electron poor. There are resonance structures in which the ortho and para carbons have positive charges on them. So from that perspective, the nitro group is a meta director. Two basic reasons for that. Having the nitro group on causes in the intermediates causes the ortho and the para substituted intermediates to be less stable because the ortho and the para substituted intermediates place positive charge adjacent to the nitro group, which is an electron withdrawing group. Having a positive charge adjacent to another positive charge, that should look bad, and it is. It's destabilizing, it's repulsive. Repulsive but not disgusting, I guess. The second reason is to notice that the nitro group is an electron withdrawing group by resonance, which tells you that the ortho and para carbons are less reactive to begin with than the meta carbon. So for the meta directors, we see the meta substitution product not because the withdrawing group is stabilizing the positive charge, but because it's just not destabilizing it as much as for the ortho and para positions. So the argument for the donating groups is ortho and para substitution intermediates are better and more stable. For the electron withdrawing groups, the argument is the meta substitution intermediate is just less bad. Okay, questions about that? So you've seen a withdrawing group that's a meta director. You've seen a donating group that's an ortho para director. This donating group is a donating group via via an inductive effect. We said that here. I want to show you briefly a donating group via resonance. So the classic example of that is like an aniline or a phenol, something with a heteroatom that has lone pairs on it. Let's just use a methoxy group. If you were to do the subsequent nitration reaction, you would find that, and I'm just going to draw the products that are preferred at this point, not the minor products. You would see the ortho and the para substitution products. You would not necessarily expect the ortho and the para substitution products to form in a 1-to-1 ratio. You would expect to get both of them. There's not really a way around that, and you would hope and assume and you can assume this, that in synthesis you can go on to do the next step after having separated the ortho and para isomers. The reason for ortho and para substitution here is going to be the same as we saw earlier. I'm going to just draw you the ortho, I'm going to draw you the ortho intermediate, and then I'll leave the rest to you to show how the ortho intermediate is better than the meta intermediate. But notice that in the ortho substituted intermediate, the positive charge can be adjacent to the methoxy group. And that actually allows me to do a resonance structure in which lone pairs on the oxygen donate in to form a new pi bond between oxygen and the carbon of the benzene ring. That spreads out the positive charge by resonance, meaning there's another place the positive charge can be. That stabilizes the carbocation intermediate, and it makes, therefore, forming the ortho substitution product and the para substitution product faster. The methoxy group is an example of an electron donating group via resonance. And for methoxy groups, these are generally ortho and para directors. You see only the ortho and the para products. Yeah?
One thing I find a little confusing is that they're selective for where the positive charge is placed during resonance, the most stable place to put the positive charge.
Right.
But the benzene rings nucleophile
Right, yeah, so the question is, these reactions all involve the benzene ring being a nucleophile. And so all we have talked about so far is the impact of having a group already on the benzene ring on the regioselectivity. We haven't talked about the rate of the reaction relative to benzene, and that turns out to be sort of a separate issue. And it's kind of complicated, but we do need to talk about it. And I guess before we do, notice that some groups, like the methyl group, are just exclusively electron donors via an inductive effect. There's no opportunity for resonance. Some groups, like the nitro group, are electron withdrawing groups by both the inductive effect, because nitrogen's more electronegative than carbon, and through resonance. And then there's others, problematic, that are electron donating groups via resonance, but, and I'm afraid to write this down because it's going to be confusing to you, but it is reality. So the oxygen is actually an electron withdrawing group via an inductive effect, meaning oxygen's more electronegative than carbon. What we're talking about with the inductive effect is actually about a bond dipole, a tug of war of electrons that are shared between two atoms. You might expect the electrons in this oxygen-carbon sigma bond to be polarized towards the oxygen, and that's true. The resonance effect focuses on the lone pairs. That's a different pair of electrons. So a single group can have dual character, and sometimes what you observe involves these two effects, the resonance effect and the inductive effect, offsetting each other. And so how do you deal with this? Your text actually ranks the groups that are attached, that can be attached to a benzene ring in terms of how electron donating they are versus withdrawing, and that can be helpful. Before we get to that, though, you should understand that there's a difference between being an ortho. The issue of regioselectivity is an issue of, do we see ortho-para versus meta products, isomers. The second issue that we've talked about is, what does the group do to the nucleophilicity of the aromatic ring? Is it more reactive, and your text will use the term activated, or less reactive, deactivated versus benzene? So, and those are sort of two separate issues, and you're going to need to keep them separate because you're going to see that there's actually one group of things that can be attached to benzene ring, the halides, which deactivate the benzene ring or lower its reactivity relative to benzene. I'm worried about these activated and deactivated because I'm worried that you see deactivated and you think like Star Wars droids, they're now dead and don't do anything. We just mean less reactive. You're going to see that the halides make the benzene ring react more slowly, but they're also ortho and para directors. That's a weird one. It's probably one you're just going to have to memorize. What we'll do now is I'll show you the kinds of groups that can be attached to benzene rings. We'll talk about whether they're ortho-para directors. We'll talk about whether they're greater or higher or lower reactivity versus benzene. So over here we're going to have the substituent. So these are amino substituents where you've got the squiggly line indicates that's the attachment point to the benzene ring. You need to have a lone pair on the nitrogen. Generally R here is alkyl. These are the so-called anilines, and they are electron donating groups via resonance. They are actually, they would qualify as electron withdrawing groups via an inductive effect. You can rank how strong the inductive effect is by looking at the electronegativity of the atom that's attached to the benzene ring. You can also sometimes rank the ability of an atom to be a resonance donor with electronegativity as well. The more electronegative an atom is, the less willing it is to share its electrons, the less good of a electron donating group it should be by resonance. Which is why we are ranking the anilines higher than the phenols. So slightly below the anilines, we could put the OH group and the OR group. Ethers attached to benzene rings happen to be called anisols. You don't need to know that, but there it is. These are likewise electron donating groups via resonance. They should be slightly worse at donating than the nitrogens, because oxygen's more electronegative than nitrogen. And they should be slightly more withdrawing from the perspective of the inductive effect. Now, how does that impact regioselectivity? Both of these are ortho and paradirectors, presumably because the resonance effect dominates. And in terms of reactivity, we're going to say more reactivity versus benzene, or nucleophilicity versus benzene. We're going to say more for the anilines and the phenols and the anisols, more reactive than benzene. But we're putting them in ranked order, so you'd predict the anilines to be a little bit more reactive than the phenols. Okay. Now, it turns out that we can, if you want to tune down the reactivity of an aniline or a phenol, it's pretty easy. All you do is you make the corresponding amide or ester. Why would this tend to tune down the reactivity of the aniline or the phenol? The idea here is those lone pairs excuse me, I'm not getting emotional, my voice is just hoarse. The lone pairs on the heteroatom, which are the ones that donate into the ring, are now adjacent to a carbonyl, and you can draw resonance structures where those lone pairs donate into the carbonyl carbon and out onto the oxygen. So having that carbonyl there attenuates the donating ability of the lone pair, makes it less donating, and so these are still ortho and paradirectors, but you can see they're not as big of a deal as just the straight up OH group or the OR group. Does that make sense? Questions about that? Okay, generally we find that resonance donating is more powerful than inductive donating. So the phenols and the anilines and their amide and ester derivatives show up higher on the list than the alkyl benzenes. So this would be a methyl or primary or secondary or tertiary. And these are electron donating groups via an inductive effect. simply because the sp3 hybridized carbon attached to the benzene ring is less electronegative than the sp2 carbon on the benzene ring. So these donate electron density in. These are all still more reactive than benzene, though we've got them in rank order. So you would predict that an alkyl benzene would be only a little bit more reactive than regular benzene. Okay, enter the strange dividing line, because what we're going to talk about now, everything we're going to talk about from here on to the end of the table is less reactive than benzene. Nevertheless, what we're going to talk about here is still an ortho and para director. So we must now be at a stage where we're on the cusp. We're at the switchover between a group that has electron donating capabilities via resonance, but those capabilities are sufficiently weak that its withdrawing abilities via the inductive effect start to make a difference in terms, if not in regioselectivity, certainly in terms of reactivity relative to benzene. And these are the halides, so chloro and bromo. We haven't learned how to put fluoro on a benzene ring, but you could include fluorobenzenes in this category. They are less reactive, and apparently the inductive withdrawing capability dominates and gets you that less reactivity versus benzene. But the presence of these lone pairs, when push comes to shove and you get in the carbocationic intermediate that's already positively charged, those lone pairs can still stabilize the positive charge via resonance. I will draw one such example. Here's a chloro group, here's an ortho substituted carbocation. Notice that the lone pairs on the chloro can engage in resonance donation to spread out the positive charge. It's perhaps not the best resonance structure you've ever seen. We can talk about reasons why that is, though they're probably not that important for our discussion here. But the ability to donate via resonance is what drives the ortho and para director. So what do all of these ortho and para director resonance donors have in common? Lone pairs on a heteroatom adjacent to the ring. And then the only other thing is the alkyl group. You can remember that, you're going to get the ortho and para substitution questions right. However, you will need to remember that the halides are less reactive. When you put them on a benzene ring, it makes the benzene ring overall less reactive. There are some questions in your study guide and problem set that are like, which benzene ring is more reactive than the other? And if you memorize that the chloro is an ortho-para director and you forget that it's also an electron withdrawing group via an inductive effect, the outcome of those problems isn't going to make a lot of sense to you. Okay. The halides are the weird ones. Everything else that we see on the list are going to be both less reactive than benzene and metadirectors. So we're going to see that mostly these groups are all electron withdrawing groups via resonance. Some of them will also be electron withdrawing groups via an inductive effect. So basically carbonyls adjacent to a benzene ring. And I want to distinguish what we're doing here from the amide and ester examples earlier. In the amide and ester examples earlier, it was the heteroatom with the lone pair on it that was attached to the benzene ring. Now we're talking about attaching the carbonyl carbon to the benzene ring. Ketones, aldehydes, carboxylic acids, esters, yes, esters, but only if the carbonyl is attached to the benzene ring, and amides, even amides, but only if the carbonyl is attached to the benzene ring. These are all meta directors. Like nitro, they are electron withdrawing groups via resonance. You could see that. I'll just draw you one resonance structure, not of the intermediate, but of the starting benzene, that shows you how we can draw a resonance structure in which we put positive charge on the ortho and the para carbons. And so as with the nitro group, so these carbonyls tend to lower the nucleophilicity of the ortho and para carbons. You could consider these carbonyls as also inductive withdrawing groups in the sense that you've got an electronegative atom not directly attached to the benzene ring, a little bit further away. The further away you go, the weaker the inductive effect is. I would say the major contribution here for the carbonyls is the resonance electron withdrawing. And then, also on the list, and we don't need to belabor the point, the sulfonyl group that we've attached to the benzene ring, and then I've already described the nitro group in detail. These are electron withdrawing groups via resonance, and they are also meta-directors, and they are also less reactive than the benzene ring. Okay. So this gives a tour of things you can attach to benzene rings. The rank order is important because sometimes we're going to find ourselves in a situation where we already have a couple of groups on a benzene ring. We want to do a third reaction, and we're going to need to decide what happens next. All right, with this in mind, that's a reasonable stopping point. Let's take like 5 minutes, and then we'll come back and spend the rest of our time practicing synthesis.